In the last lecture, we got the mathematical formulation of the physical laws of electromagnetics, that were the Gauss law, Ampere's circuit law, and Faraday's law of electromagnetic induction. The compilation of these physical laws in mathematical form are called the Maxwell's equations. So, Maxwell essentially compiled these laws, gave the mathematical representation. However, while doing this, he found a difficulty. He found there was inconsistency in the Ampere's circuit law. Let us understand what was the difficulty which was encountered by Maxwell while compiling these equations. So, let us consider a closed surface of certain volume, let us say V, and let us say these are charge distributed inside this surface. Then there is a possibility that the charges might leave this surface, and when the charges will leave, there will be a rate of change of charge. So, there will be current flow from the surface. So, we will have a current density distributed on the surface, and whatever charges will be leaving in the form of current, that should be reflected in the reduction of the net charge inside the surface. So, let us say we have the conduction current density on the surface, which is given by J. Then, as we saw from the concept of divergence, that if we take this vector field J, the divergence of J essentially is a net flux coming out of this volume. So, if I just take the divergence of J, that essentially should represent like the outflow of this vector field, which is the conduction current density. Before getting into that, let us say that I have a small infinitesimal area on this surface, which is given by dA. So, if I take the dot product of conduction current density and the area, that gives me the outward current from this infinitesimally small area, and if I integrate that over the entire surface, I get the net outward current from this surface. So, I have here from this surface the net outward current, which is nothing but integrated over the closed surface. Let us say this surface is S, the conduction current density over that infinitesimal area. So, this integral, as we saw earlier also, that it represents the total current coming out of this surface, and as we know, the current is nothing but the rate of change of charge, and since this current is coming outward from the surface, it should be equal to the rate of charge from this volume, and since the current is coming outwards, the net charge must be decreasing inside this volume. So, if I say that this volume is having a charge density which is given as rho, and this is the conduction current density, then the net decrease or rate of decrease of charge inside this volume must be same as the total current which is coming from this surface. So, if I have the charge density rho, then the total charge enclosed by this surface will be the integral of rho over the volume. So, if I take now the rate of decrease of charge, rate of change of charge, in the volume, that quantity will be equal to minus d by dt for rate of change of the total charge enclosed in this volume. So, that is the triple integral rho into dV. What we are now saying is that simple by definition of the current, that is the current means the rate of change of charge. This net flow of the current from this surface, that should be equal to the rate of change of charge from this volume. So, essentially from this we get that the closed surface integral over S, this is over volume J dot dA, that is equal to minus d by dt of integral over the volume rho into dV. If I say the volume is not changing with time, as we assumed earlier, we can say the charges are changing as a function of time, the volume is fixed, we can interchange the integral with dt. So, that quantity that we can get as minus integral over the volume d rho by dt into dV. Now, as we have done earlier, we can convert this surface integral into the volume integral by applying the divergence theorem. So, this thing by applying divergence theorem we can write as from the divergence theorem or using divergence theorem, we can get this integral as the volume integral V del dot J dV, that is equal to minus the triple integral over the volume d rho by dt over the volume. Now, I can bring this term on this side and write the integral as the triple integral over the volume del dot J plus d rho by dt over the volume, that should be equal to 0. And as we did in other equations, since this relation should be true for any arbitrary volume, this quantity must be identically 0. So, the integrand must be identically 0. So, from here essentially we get that del dot J, that is equal to minus d rho by dt. This equation is called the continuity equation. So, if you have the time varying charges, then this quantity is a finite quantity, and then the divergence of the conduction current density is not 0. If you take a static case where the charges are not changing, then the divergence of the conduction current density is identically 0. And that makes physically sense, because if you are saying the divergence of J, as we saw earlier from the concept of divergence, the divergence tells you the net quantity coming out of this volume, and if the net current is coming out of this volume, that means there must be net charges must be leaving this volume. So, there must be a change in the total charge or the charge density inside that volume. If the charges are not changing inside the volume, then whatever charges are entering the volume, those charges must be leaving. So, the net charge inside the volume remains same, and in that case the divergence of the conduction current density is equal to 0, because there is no net flow from this volume for the current. So, whenever we are having in general the time varying quantities, the continuity equation must be satisfied by the conduction current density and the charges. Precisely this was the equation which led difficulties for compiling the other equation by Maxwell. And let us see what is the problem. We have seen earlier that from the Ampere's circuit law, we get an equation which is del cross H, that is equal to J. So, the curl of the magnetic field is equal to the conduction current density. If I simply apply the vector operation on this without getting into physical aspects, we can simply say I can take the divergence of this equation on both sides. So, I can say divergence of curl of H is equal to divergence of J. So, if I just take divergence, I will get from this relation del dot del cross H, that is equal to del dot J. We know in the vector product we can interchange the sign dot and cross. So, this thing can be also written as del cross del dot H equal to del dot J. Now, this quantity is identically 0. So, this quantity is identically 0. What that means is, from the Ampere's circuit law, that the divergence of J is identically 0. That is the precise problem, because it is inconsistent with the continuity equation. The continuity equation says that the divergence of J has to be negative of rate of change of the volume charge density, whereas the Ampere's circuit law says that the divergence of J must be identically equal to 0. So, basically the Ampere's circuit law does not satisfy the continuity condition. Precisely that is what was the difficulty which was encountered by Maxwell, and he resolved this difficulty by introducing the concept of what is called the displacement current density. So, what he said is, if I have this rho and I go to one of the Maxwell's equations, and if I replace this rho from the Gauss law, which says that the rho is the divergence of the displacement vector d. So, I can write this quantity as del dot d from the Gauss law. So, if I substitute for the charge density rho from the Gauss law, we have del dot d is equal to rho. So, I can substitute for rho in this equation. So, I get del dot J is equal to minus d by dt of del dot d. Interchanging the operators, space operator and time operator, this will be minus del of dot of dd by dt. I can bring this thing on the left side and integrate over volume. Sorry, this is del dot J plus del dot d by dt dV, that should be equal to 0. From here, again using the divergence theorem, this thing can be written as over the surface area A, J plus dd by dt into dA, that should be equal to 0. What we are now saying that is that the current which is coming from this surface, which we saw the closed surface, is not only this current which is the conduction current, but there is some quantity which is also having dimensions which are the current density dimensions. However, this is the rate of change of the electric displacement. So, dimensioning, if I look at this quantity is same as the current density. However, this quantity does not depend upon the conductivity of the medium. We have seen earlier that the conduction current density is related to the conductivity of the medium. From the Ohm's law, it is sigma into E. However, even if the conductivity of the medium is 0, then we have a quantity which is rate of change of the displacement d, and that quantity is equivalent to some current, and since this is related to the displacement vector d, we call this as the displacement current density. So, this quantity is the new quantity which was introduced to satisfy the continuity equation, and that is called the displacement current density. Once we say that, then what we are saying is now the net current which we are talking about is not only the conduction current, but it is the conduction current plus the displacement current. And then Maxwell said, if you incorporate this term appropriately for defining the total current, then the Ampere's law can be modified to say that the magnetomotive force around a closed loop is equal to the total current enclosed by that loop, which includes the conduction current as well as the displacement current. So, earlier, since this concept was not there, the current always meant by the flow of the charges. However, in this case there is no flow of charges, because even if I do not have charges, still I will get this quantity, because this quantity d is related to the electric field. So, if I have an electric field which is time varying, this term will be equivalent to a current flow. So, this quantity which is simply representing the rate of change of electric field represents a quantity which is equivalent to current. So, if I take the total current, which is a combination of the conduction current, which is because of the movement of the charges and because of the time varying electric field, then this total current is equal to the magnetomotive force around the closed loop. And once you do that, then this equation of the Ampere's circuit law is modified, because now this current is being changed to the conduction current density plus the displacement current density. So, once you get that, then the Ampere's law now has been modified to del cross H, that is equal to the conduction current density as we had earlier, plus we are having now additional term which is d by dt. That essentially resolves the difficulties which were faced by Maxwell, and now this gives you the complete description of the phenomena of electromagnetics. So, essentially now the four equations which we have got, the Gauss law equation, the Gauss law equivalent applied to the magnetic field or magnetic charges, the Faraday's law of electromagnetic induction, and the Ampere's law appropriately modified to accommodate what is called the displacement current density, makes the complete set of equations which represent the static and time varying electric and magnetic fields. So, these equations are called the Maxwell's equations. So, as we mentioned earlier, the Maxwell's equations can be written in the differential form and they can be written in the integral form, and depending upon the suitability, the equations can be used either in differential form or they can be used in the integral form. So, we finally write the four Maxwell's equations. We can write this in two forms. So, we can get these equations in differential and integral form. So, I write here differential form, or I can write this equation in the integral form. So, if I go to the first equation, which is the Gauss law, that gives you del dot D, that is equal to rho the same equation when written in the integral form, it says that d dot dA over the surface, that is equal to the rho into dV. The second equation when applied to the magnetic charges, that gives me del dot B is equal to 0, and that can be written in the integral form as B dot dA, that is equal to 0. The third equation, which is Faraday's law of electromagnetic induction, that gives me del cross E, that is equal to minus dB by dt. In the integral form, it can be written as integral over the contour E dot dl, that is equal to minus dB by dt dot dA. And finally, the Ampere's law, which we have got after introducing the displacement current density, that is del cross H will be equal to J plus dd by dt. And the integral form, the same thing is over this contour H dot dl, that is equal to the total current enclosed. So, that is J plus dd by dt into dA. So, now these are the set of equations which govern the total phenomena of electromagnetics for static as well as time varying fields. So, once you have these generalized equations which are for time varying fields, we can reduce the equation for the static fields, that is by putting all time derivatives to 0. I will get the equations for the static electric and magnetic fields. So, depending upon whether the permittivity or the permeability of the medium is varying as a function of space, that means if the medium is inhomogeneous, I will use this equation. If the permittivity is constant as a function of space, then I can write the same equation as we saw earlier. I can take epsilon out and I can say del dot E is equal to rho upon epsilon and so on. So, you may have a various forms of these equations depending upon the conditions applied to the medium, whether we are dealing with the electric field, magnetic fields, or we are dealing with the displacement vector and the magnetic flux densities and so on. And also, as we said, if we are talking about the static fields, then the time derivative should be put identically to 0. So, this quantity will be 0 for the static field, this quantity will be 0 for the static fields. So, if we consider the static fields, then this quantity will be equal to 0. So, the curl of the electric field will be always equal to 0. So, we will see depending upon application later on that we may put this quantity equal to 0 if we are dealing with the static fields. However, in this particular course, which is the course on electromagnetic waves, we are dealing with the quantities which are time varying. The static fields you would have studied in the earlier course, which is on electromagnetic fields. So, here we assume that all the fields and all the quantities which we are dealing here, they are time varying in general. So, the quantity rho, the quantity B, the quantity D, J, H, all these quantities are essentially time varying quantities. So, we will look for the solution of these equations later for the time varying fields. Now, as we mentioned earlier, that these equations which are in differential form cannot be applied in a situation where medium has discontinuity. That means, if we talk about the media interfaces where the medium properties suddenly change, the permittivity may change or permeability may change, and there the derivatives, the space derivatives cannot be defined because the medium is discontinuous. So, the differential form of this Maxwell's equations is not useful in those situations. However, as we had mentioned, the integral form is always useful and this can be applied in any situation. However, when we apply the integral form to the discrete media interfaces, we get relationship between the quantities d, b, e, h in the two media just across the interface, and that relationship we call as the boundary conditions. So, the same set of equations when written in differential form, they give you what is called point relation. So, these relations are valid at every point in space. The equation in integral form when applied to the discrete media interfaces, they give you what is called the boundary conditions. However, before we go into the boundary conditions, let us introduce a concept of what is called the surface current and surface charges. An idea is as follows. Let us say I have a surface which is having, let us say, a thickness some d. So, this thickness for this is d, and let us say I have a charge density inside this slab which is given by rho. So, I have a charge density which is rho, which as we saw is coulomb per meter cube. That is the density which we have. So, all over these charges inside this are distributed with this density. If I now consider a area which is unit area on the surface, so let us say this length is 1, this width is 1. So, if I consider a volume of unit area on the surface of the sheet, the total charge which will be in this volume, which is having a height of d and area 1, will be the charge density multiplied by the volume. So, I have total charge in this area in unit area slab, that will be equal to rho into the volume of this, which is 1 into 1 into d. So, that is equal to d. So, if the thickness is given, then I can say, if I see from the top, that is the charge I am going to see, which is rho into d in this area, which is 1 into 1. Now, let us say if I reduce the thickness of this slab and go to a limit when d tends to 0, and suppose the rho increases to infinity when this thing happens when d tends to 0. So, you will get a quantity when this is tending to infinity, this is tending to 0. So, the product of these two still might tend to a finite quantity. So, if I have a situation where the volume charge density rho is infinity, but the thickness to which this density is confined is 0, I will see a net charge which is just on the surface, because this charge is now confined to a thickness of 0 width. So, since the thickness is 0, the charge will be just lying on the surface, and that charge now is in this area of unit area. So, if I take this quantity rho into d and take a limit when d tends to 0, I get a quantity what is called a charge which is distributed on the surface, and that density will be surface charge density. So, the units for rho will be coulomb per meter cube. I am multiplying by this. So, I will get now a charge which is per unit area, and this charge truly is confined to the surface of the sheet. So, we say rho s is in the limit when d tends to 0. If I calculate this quantity rho into d, that is what is called the surface charge density. So, the two things you should note here, that if I go from this volume charge density rho to the surface charge density, when d tends to 0, if a true surface charge is there, that is equivalent to the infinite volume charge density. If that infinite density is confined to 0 thickness, that gives me the distribution of charges truly on the surface, and that is what is called the surface charge density. So, we have here what is called surface charge density, and the unit for this will be coulomb per meter square. So, we have this quantity will be coulomb per meter square. So, later on we will see that in situation like conducting boundaries, where the conductivity becomes infinite, you might get the charge density, which will volume charge density, which will be infinite, and these charges truly will be confined to the surface, and that time this concept of surface charge density will be useful. So, at the moment, without getting into which media will give me surface charge density, we can say principally we may have charges distributed truly on the surface within a 0 thickness, and that charge density we will call as a surface charge density. The similar thing we can do for the current also. So, let us say I have again this slab of thickness d, and let us say it is carrying a current which is J. Now, let us consider now thing like this. So, the current which is flowing now in this will be, this is let us say unity, this is unity. So, the total current which will be flowing through this will be J multiplied by the cross section of this, which if I see from the H side, the cross section will be d into 1. So, the total current which I am going to see under this area, that will be J into 1 into d, that is the current which is confined to this. So, for the conduction current density J, the current which will be flowing in the direction of J within the unit area on the surface will be J into d. So, if I say this is the conduction current density, I will say now the current under unit area on the surface, that quantity will be equal to J into d into 1, which is the area of cross section is 1 into d. So, that is the current which will be under this. Now, again if we make this d tending to 0, and if J goes to infinity, then again this product J into d will be a finite quantity. So, you will have a current which is truly flowing on the surface, and that current we call as the surface current. So, if I take a limit, so I define what is called a surface current density, and that is let us say given by Js, that is equal to the limit when d tends to 0, J into d times d. It is not a dot product, it is just the J multiplied by the area, and direction of Js is same as the direction of J. So, this quantity will give me a current which is flowing on the surface, and again as I mentioned, this will be true provided this quantity, the conduction current density J, is infinite. Then and then only when d goes to 0, this product will be finite, and we will have the surface current density. This again will be applicable to the boundaries which are conducting boundaries. So, when the conductivity of the medium becomes infinite, that time the current which will be sigma times E for finite electric field will become infinite, and then you will have what is called a surface current. Since the unit of the conduction current density is amperes per meter square, the unit for this will be the amperes per meter square multiplied by d, which is the length. So, the unit for Js will be amperes per meter. That is the reason this quantity is also called the linear surface current density, because this is now at the per unit length you are defining this current. So, now we are having overall the quantities like the charge density, which means volume charge density. We have a quantity like current density, which means conduction current density. We have a quantity like displacement current density. Then we have got surface charge density, and then we have got the surface current density. So, one may say these are the sources which are related to the fields, which are the electric and magnetic fields. So, in general, then one can establish relationship between these quantities, which we can call as sources, to the fields, which are electric and magnetic fields, and these relationships are called the boundary conditions. Let us now solve some problems based on the Maxwell's equations and also on the boundary conditions. So, let us consider a very simple problem based on the Gauss law. So, we see here the volume charge density inside a hollow sphere is given as rho equal to 10 into e to the power minus 20 r coulombs per meter cube. Find the total charge enclosed within the sphere. Also find the electric flux density on the surface of the sphere. So, finding the total charge enclosed inside this sphere is very straightforward. So, the total charge enclosed inside this sphere Q, that will be equal to the integral over the volume of the sphere to rho into dV. So, if you write down this volume into the spherical coordinates, this is equal to the phi going from 0 to 2 pi, theta going from 0 to pi, and r, which is the radius of the sphere, which is 2 meters. So, it is going from r is equal to 0 to 2 rho r square sin theta dr d theta d phi. So, if I substitute now for the charge density inside this and integrate over this volume, essentially we can write down this is the integral 0 to 2 pi, there is a circular symmetry over phi, then we are having integral for theta, which is going from 0 to pi sin theta d theta, and then we have integral here, which is from 0 to 2. So, integral 0 to 2 pi, then we can substitute for rho from here, that is 10 e to the power minus 20 r into r square dr. This integral is very straightforward, that will give me equal to 2 pi. Similarly, the sin theta integral is also very straightforward, it will be minus cos theta, and if I substitute for the limits of theta and phi, then I can get the total integral for this, that will be equal to pi divided by 100 coulombs. So, the total charge enclosed inside the sphere of radius 2r with circular symmetry with the charge density, which is given by this, is pi upon 100 coulombs. Now, to find out the electric flux density on the surface of the sphere, essentially we can make use of the Gauss law, which states that the total electric displacement from a closed surface is equal to the total charge enclosed by that surface. Now, in this case, since the surface is a spherical surface and since the charge is distributed in a spherically symmetric manner the electric displacement will be uniformly distributed on the surface of the sphere. If I consider the sphere like that, the electric displacement will be uniform all across the sphere. So, now we can find out the electric displacement on the surface of the sphere, which is nothing but the total charge enclosed, which is this charge q, which is pi upon 100. So, if you want to find out what is the electric flux density on the surface of the sphere, essentially we have 4 pi r square, where r is the radius of the sphere, multiplied by the density is equal to the total charge enclosed, which is q, which is equal to pi upon 100. So, from here we can calculate the electric flux density on the surface of the sphere, which is equal to q upon 4 pi r square, and substituting for the value of q, which is pi upon 100, and r is equal to 2 meters, we get electric flux density on the surface of the sphere equal to 6.25 into 10 to the power minus 4 coulomb per meter square. So, in this simple problem, the electric charge density was given inside a spherical volume, and we were to find out the total charge enclosed in that volume, and also the electric flux density on the surface of the sphere. Let us consider another problem, and let us say now the problem is that the electric flux density is given as d is equal to x cube x cap plus x square y z cap. So, now the electric field or the electric displacement density is given in the vectorial form, and we have to find the charge density inside a cube of side 2 meters placed centered at the origin with its sides along the coordinate axis. So, now we can apply the Gauss law in the differential form to find out first the charge density, and once you get the charge density, then we can find out the charge enclosed right inside the cube. So, firstly we can go, we know from the Gauss law that the del dot D is equal to the volume charge density rho. Expanding this in the Cartesian coordinate system, we get d dx by dx plus d dy by dy plus d dz by dz, that is equal to the volume charge density in that region. Substituting now for the d which is given here, where the x component of d is x cube, y component of d is 0, and z component of d is x square y. If I substitute this into this expression, essentially we find that rho is equal to d by dx of x cube, the y component is 0, so this quantity is 0, plus d by dz of x square y. Even this quantity is 0, because d by dz of this quantity x square y will be 0. So, essentially rho will be d by dx of x cube, which is equal to 3 x square. So, now inside the volume of the cube, the charge density essentially varies only as a function of x, and the charge density is constant as a function of y and z. So, now if I have a coordinate system, the cube essentially is placed something like this around the center, and then we want to find out what is the total charge enclosed inside this cubical volume. So, you can get the total charge enclosed Q, that will be integrating this charge density over the cubical volume, that will be equal to minus 1 to 1, minus 1 to 1, minus 1 to 1, rho into dx to dy dz. Substituting for rho in this, that will be minus 1 to 1, minus 1 to 1, minus 1 to 1, 3 x square dx dy dz, which we can write this quantity integration with respect to y will give me 2, with respect to z will give 2. So, essentially we have here 12 minus 1 to 1 x square dx, which is nothing but equal to 12 into 2 upon 3, which is equal to 8 Coulomb. So, in this problem, the electric displacement density was given in the vectorial form, and by applying the same Gauss law in the differential form, essentially we could find the total charge enclosed inside a volume. Let us consider now a problem which is related to the magnetic fields. So, let us say now the problem is in a conducting medium, the magnetic field is given as H is equal to y square z x cap plus 2 into x plus 1 y z y cap minus x plus 1 z square z cap. Find the conduction current density at point 2 0 minus 1 meters. Also find the current enclosed by a square loop which is defined by y equal to 1, x between 0 and 1 and z between 0 and 1. So, essentially this loop is lying in the xz plane at a height of y equal to 1. So, we have to find out the conduction current density at a point because of this magnetic field which is given in the space. So, essentially we want to use the Ampere's law in the differential form to find out the conduction current density. So, if you go to the Ampere's law, we know that the Ampere's law is given as J is equal to del cross H. In the Cartesian, if we expand this curl operation, that will be the determinant x, y, z, d by dx, d by dy, d by dz. And if I write down now the component of the magnetic field which are given here, which is y square z 2 into x plus 1 y z minus x plus 1 z square, then I can get here y square z 2 into x plus 1 y z minus x plus 1 z square. And if I expand this, essentially we get the conduction and density in the vectorial form, which will be minus 2 x plus 1 y x cap plus y square plus z square y cap. So, at location two 0 minus 1, the conduction current density J will be equal to, if I substitute now x equal to 2, y equal to 0 and z equal to minus 1, the conduction current density will be 1.0 y cap. Once I know the conduction current density, then I can go and find out what is the total current enclosed by the loop which is defined by y equal to 1 and x going from 0 to 1 and z going from 0 to 1. So, if I look at this in the yz plane, this is the, or xz plane, this is z is going like that, x is going like that. So, x is going from 0 to 1, z is going from 0 to 1. and now the conduction current density is oriented in the y direction. So that means if I go by the right hand rule, the z, my fingers, if I point from z to x, the thumb should point to the y direction. So essentially the conduction current density within this is essentially given by that. The current is coming out of the plane of the paper. So now the total current enclosed by this I, that will be integral j dot ds, which is nothing but the integral j dot y cap to dx dz. So if I substitute now for the limits, the x goes from 0 to 1, z goes from 0 to 1, and the current now will be only jy, because dot product of j and y cap will be jy dx dz at y equal to 1. So substituting now for the conduction current density, in this essentially we get this integral with the same limits 0 to 1, 0 to 1, 1 plus z square, because you are substituting y equal to 1 in this, dx dz. If I solve this integral, I get the total current enclosed inside this loop, which will be 4 upon 3 amperes. So in this case, we are using the Ampere's law in the differential form. The magnetic field was given in the differential form. Then by using the Ampere's law in differential form, we find out from the curl the conduction current density. And once you know the conduction current density, then we can find out by integrating over the area of the loop the total current enclosed by the loop. So these are some of the very simple problems which essentially give you some feel for how to apply in practical life the laws, the physical laws like Gauss law or the Ampere law, either in differential form or in integral form.